Hi, my name is Ron Dorn. I'm here to explain to you the hours GPH211 project for fall of 2023. So I'll do this by sharing screen so you can see the presentation I have. Um, the hours project is for online students in the College of Liberal Arts and Sciences to get involved in research. And in the GPH 211 geomorphology class, um, the idea is to swap out one for one the longer labs that make up 40% of your grade with this project. And so I'll review some of the key aspects of how ours relates to our class. It's asynchronous. As with all aspects of ASU Online, you won't have to bend or juggle your crazy schedule to match others. There will be an option for coordinated group meetings, but that's not a requirement. Um, how does it connect to GPH 211? The part of your grade that involves doing longer multi-step labs is a swap, a complete substitute. So you can look at the lab choices in the Canvas shell and decide what interests you most. You can do the longer labs and hours also and just pile up the points, but it won't improve your grade. It'll just be an additional experience. There are no prerequisites. I assume you have no prior background in any of this. Geomorphology is a field of science with really few scientists. And so there's a lot of very basic research left for new and enthusiastic students to help. I think you can make real research contributions being new geomorphologists. Publication is an intent of this project, but it's not part of ours. The timeline for getting research published in a journal is much longer than the 7.5 weeks of the 211 class. So you can decide if you want to continue the research process and be an author, or just stop and be acknowledged on the paper. So the agenda in this presentation is to explain the basics of the research question and project, explain what each student will do in the research to receive full credit. After the class, how to work towards a publication and why publish, and then a lot more background on the geomorphology of the research question. The people helping you are myself, Ron Dorn. I'm a professor, arrived at ASU in 1988, and Michaela Roberts, who currently is a GIS major, but she already has a lot of experience doing geomorphic research. So we're a team helping you. Eventually, when the paper gets published, I hope Michaela will be the first author. So the research question is, how do tributary drainages develop over a period of 5 million years? And now I know you don't necessarily know what a tributary drainage is. I'll explain. So project part one would be selecting a drainage area in the region of the Canyon Apache Lakes area and analyze its characteristics. The analysis can be completed with a technique that others have used, or you can develop your own approach. We'll model a few examples for you. You won't be left to dangle. Project part two, compare results from students studying different drainages, and we'll analyze similarities and differences. And we'll reveal strengths and weaknesses of different research strategies used in part one. And then in part three, we'll go back, figure out what's the best approach, and reanalyze all the tributaries. Part four, write up of your drainage. Using a template that I provide you, you'll write up the methods and results of your tributary drainage. So for the 150 points, which is the largest number of points possible for the multi-step labs, part one, two, three, and four are distributed as follows. So if you stop after part one and get 75 points, that's just great. If you go through and get all 150 points, that's great. I've designed this so you really won't be fearing failure. You won't be worried about your grade doing this. Sorry about the cough there. I might cough periodically. I've got a cough going. After the class, what's done so that we can all publish this? Michaela and I will select a fast journal to help your research record, but it's still a slow process. So the first thing that'll happen is we'll establish authorship and select the journal. And the journal sets the format of the article. Michaela Roberts is the lead author. I'm the last author, and the order between the two will either be alphabetical if everybody did a similar amount of work, or I'll decide based upon observations of who did the most work, the author order. We'll write a study site and regional setting. We'll dig into the prior research on the project, and you'll learn how to write a discussion section, which is like having your results go out to have a coffee or lunch or a beer with the prior research. Some people think that it's important to write what's called a literature review. We'll do that in the context of comparing it to our results. Then we'll write the methods, and then we'll write a section called Background on Tributary Development from Base Level Lowering versus Tectonic Uplift. And then we'll finish the rest of the stuff, the introduction, conclusion, abstract figures, tables, cover letter, and we'll submit it. And then after we submit it, we'll get reviewed and we'll have to revise and resubmit. Okay, now a lot more background on the research question. The Salt River system is complicated. The upper left-hand corner is a graphic done for another publication on different components of the Salt River system that flows through metropolitan Phoenix. And then the lower left diagram shows different structural basins. Basically, these are low spots that were tectonically faulted down that the Salt River system had to somehow fill in and then be able to flow across. So what happened is that the presentation you already watched, perhaps 65 minutes long, is revised. The Salt River didn't arrive 2.5 million years ago. It developed 5 million years ago. And so I'm going to explain the new findings, the timeline of how the longitudinal profile of the Salt River developed and influenced the base level of tributaries, discuss implications of the new findings, show you how some others have done research on tributary drainages, what's special about our study area, what's the key to why I think this can get published, and then suggest how you can look around the study area and think about what you might want to do. So the unpublished new findings revise what was presented earlier. We did research with a group of us, Steve Scott-Nicky, Jerzy DePani, Brian Gauthier, Yang Xiang, Phil Larson, Ara Zhang, big team to understand what happened to the arrival of the Salt River. And we first thought that the Salt River, when it arrived over Granite Reef Dam, started flowing down the East Valley, that it was flowing towards a low spot down by Gilbert, and then it filled up this East Valley. We have a burial age of 2.77 million years with a big plus or minus for the earliest arrival time of the Salt River in the East Valley of the Phoenix metropolitan area, and the sediment beneath it was 3.9 million years. This is wrong. It's been revised because Yang Xiang did some burial dating, cosmogenic burial dating work, and I'll explain the method later if you decide to join us. It's reasonably complicated, that the Salt River arrived based upon well cuttings collected from around 140 feet deep near the airport, Phoenix Sky Harbor Airport, that the Salt River gravels arrived over 5 million years ago. They started filling in the area at a different well in the airport area. There's an age of 3.71 million years ago. So we know the Salt River was flowing towards the airport, not towards the East Valley, about a little over 5 million years ago. So here's a strange plot that Mark Schmeckley made, who's a geomorphological colleague on this. is that, um, let me see, the upper right-hand corner shows Papago Park, and this is Tempe Butte. And here's the data from the Salt River Project on the pre-Salt River surface. This pre-Salt River surface is shown in a grid using GIS for what the topography looked like when the Salt River arrived. This blue down here is the low spot where we thought the Salt River went. This dotted line is the modern Salt River. And so the low spot when the Salt River started to flow through this region was actually a swale, a broad area between a fan coming out of the Pima Wash of South Mountain and Papago Park. Right up here is Tempe Butte. So the Salt River swung around and started depositing gravels at about 921 feet over 5 million years ago. The gravels deposited and reached an elevation of between 981 feet and 1,036 feet. So somewhere in this time range is where the 3.71 million year age gets from. That's just about the same elevation as that what would be required really close to flip the sediment down to Chandler and Gilbert in the East Valley. So this project that you're working on is not working out how the Salt River went first to the airport and down to the East Salt River Valley. It's the consequences of the Salt River being over 5 million years old. So here's some graphics. In the upper right-hand corner is a cartoon made by a student, Ariel Shamas, who took GPH211, and she wanted to use her artistic talents to present a fantasy world of what the region would have looked like before the Salt River was there. And so here's the Four Peaks region. This is the McDowell Mountains, the Ussery Mountains, the Goldfield Mountains. There was a playa, or a flat surface of a dried lake up here, Bartlett Lake, Horseshoe Lake, Verde River Valley up here. And so when the Salt River started flowing over the Four Peaks area, none of this eroded topography was there. And there was a giant alluvial fan that the Salt River was flowing on top of, and it just simply flowed in the low spot of this alluvial fan towards the airport. And so here is the Salt River floodplain today, and the Gila and the Agua Fria and the Hassayampa and Centennial Wash. Here are the locations of the ages of over 5 million years and 3.7 million years. We also have new burial ages way down here at Painted Rock Reservoir that indicates the Salt River had reached this area by around 4.65 million years ago. So there's a good amount of evidence for the Salt River's early arrival. So the timeline that concerns us as geomorphology is what's called the development of the longitudinal profile. The longitudinal profile sounds fancy. All it is just a plot of elevation versus distance of a river. So here is the Kashmir Lake in the Himalaya Mountains, where there was a case of lake overflow. And this is air pollution that kind of shows you what the lake would have looked like. Here, for the Salt River, we have to fantasize a different way. Somewhere in the area of Roosevelt Lake, there was a big giant lake, and there was a spillover. The spillover set the Salt River in motion, flowing on an alluvial fan deposit. And there are 4 different ways that a river can get across a mountain range, like the Marazal Mountains. What we think happened is what's called overflow. So you can think of the Salt River as being non-existent. It simply wasn't there. There were alluvial fan deposits. There were some small channels, and the Salt River just spilled over at a low spot, and it had a very steep profile to start with. And eventually, the Salt River was able to cut through the mountain range and establish a lower gradient profile. In here, time step 2. That's what's meant by the development of the longitudinal profile. So this is the Four Peaks area. Here's Apache Lake. Back here is Roosevelt Lake. And here's the current Salt River. And all of this area in here on the right-hand side of this view taken by Steve Skotnicki is eroded in the last 5 million years. The Salt River was in an elevation way up above this ridge right here. This was part of the alluvial fan system that the Salt River started flowing on. So everything you see to the right has eroded in the last 5 million years. All of these rivers called tributaries that cut back up into the mountains developed in the last 5 million years. This one, this one, this one down here. So we have not yet published the 5 million year old age. We're working on it. This paper that we're doing here is a follow-up to the implications of the Salt River's arrival 5 million years ago. Because we have this timeline, we can think about areas like this, which is the superstition volcanics that are eroding. We know that this drainage area is younger than 5 million years, or about 5 million years old. And there have been so many changes to the Salt River in the last 5 million years. Here is an area where a lot of people go tubing in the Phoenix area. So there are these things called river terraces that reflect positions of the Salt River as it's cutting down. There's a big feature called Stewart Mountain Terrace, which is a remnant of the old alluvial fan gravels that's up here with some river deposits on top. Our research project is not the story of the longitudinal profile or the story of when the Salt River arrived. We're going to have fun picking the low-hanging fruit of studying tributary development. So here's Canyon Lake. Here's Apache Lake. Everything you see to the right and left of these lakes, we know when the clock of erosion started. We have a good estimate for how high up that area was of bedrock completely uneroded. So what you're seeing here is something to make geomorphology professors drool. They would love to have this sort of a project to work on because people have been working on the topic for a long time. Here are just snippets of titles of papers. Causes of concavity in the longitudinal profile of streams. Concavity is where the river has a flat profile way down low and it gets really steep up high. Post-lacustrine means after lake evolution of a tectonically controlled basin in southern Italy, bedrock rivers, and the geomorphology of active mountains, drainage patterns and their significance, erosional development of streams and their drainage basins, transient landscape and stratigraphic responses to drainage integration. These are the sort of papers that we will, when we're writing this all up, be working on in the discussion section and in the introduction. They are not a part of what you will be doing. We can have discussions about what others have found, what others have done, but that's not the fun part. The fun part is just figuring out how this landscape changed. So to give you an idea of what 5 million years means, let's jump to a pretty recent geomorphology example of a new river that started about 18,000 years ago. The research of Norman Meek established that the Mojave River, starting in the San Bernardino Mountains, reached a big lake called Lake Mannix about 18,000 years ago. And here's Lake Mannix. And here's the Mojave River. And this teeny tiny tributary in B is what's happened in 18,000 years. This is kind of the equivalent of what we'll be doing. The Mojave River reached Afton Basin, cut this canyon, just like the Salt River reached Roosevelt Lake and cut a canyon. And then all the tributaries struggled to keep up. So this is what this little teeny tiny baby tributary did in 18,000 years. Here's a much bigger system in what's called the Tacoma Basin over a 2 million year period. So let's look at the outlet. This basin breached, a river system developed, and here's a tributary system that's developed in 2 million years. So you're thinking to yourself, okay, so there's a timeline involved. There's also the area of the tributary basin that provides power and flood to cut things down. And then there's the Rio Grande River, which started 8 million years ago. And here's its longitudinal profile, sort of a concave up thing. And tributaries developed off of the Rio Grande. The Colorado River itself started 6 million years ago. And way up in the Grand Canyon, you can see the Colorado River, and all of these tributaries developed just in the last 6 million years. So we have some fun examples of when rivers started to develop and when tributaries developed. But right now, making a study possible is nobody else knows this timeline. It's not published. So we'll be the first people to think about how the tributaries around Canyon Lake and Apache Lake evolved over 5 million years. Most of the scholarship, most of the papers involve tectonics, lifting up mountain ranges by faulting. But we know that there's no tectonics involved. The mountains were already high, they were eroding, and our tributaries developed because the Salt River started slicing a new canyon. We kind of understand the climate of the region over the last 5 million years. And what's great is we have the rock types already mapped. And so we can look at different rock types and how the rock types affect basins. For example, in this Google Earth view, this is mapping by the Arizona Geological Survey. You have this area here being granite, this being metamorphic, and this being sedimentary. In this region here, we have some volcanics, some granite, and some metamorphic. In this area here, we've got a different type of metamorphic rock, deposits that are old alluvial fan, volcanics, both basalt and explosive superstition mountain volcanics, and granite. So there's such wonderful variety where you can pick a basin with a particular rock type and we can compare it to another rock type. So here's some speculation of what the research publication might look like. The title might be 5 million years of tributary drainage development via base level lowering, exploring the influence of rock type in a semi-arid setting. So I'm going to allow you to pause this presentation and read it rather than have me read this to you. Because these are just possible fantasy world speculation of what this paper might look like. That way you can pause the YouTube presentation and look at it at your leisure. So you'll have myself and Michaela to help you. And this in a nutshell is what the project is. We kind of sort of know when the Salt River arrived. It started and then it cut deep canyons. This is where Roosevelt Dam is located. And this is before Roosevelt Dam. So all this area here, the Salt River incised. And as the Salt River incised, all of these tributaries started to develop basins. You'll pick a tributary, we'll discuss it, we'll figure out how to analyze it and have lots of fun and do some brand new research. Thanks for listening.